We are going to look at chapter 13 this week, where we're going to talk about vector valued functions. So last week we talked about vectors and how we could define those by either an initial and terminal point or by just the terminal point with the assumption that the initial point is the origin and its component form there. And we talked about how we could have either two-dimensional or three-dimensional vectors. And then we did also introduce that idea of I, J, and K as being the unit vectors in each direction. And essentially that's what vector valued functions are going to do, is define them in terms of I, J, and K as an equation. And then we can do calculus on those equations. So we're going to start out by talking about curves in space and tangents. Tangent being a calculus idea there. So in a vectored valued function of three dimensions, we have this r. So our position vector is named r. When we were working with x's and y's, our position vector was always s. In vectors, the default letter that we use is r. So we have this vector defining the position of a particle moving through space as a function of I, J, and K, which defines its x motion, its y motion, and its z motion, kind of in that connection to parametric functions. So we can end up with some really crazy motions through space then. The first one kind of spiraling up, but taking dips in that spiral. The second one kind of looks maybe like a horse saddle type idea. And then the third one like a spring. So we can see the equations there. So just as some examples of different kinds of functions that we could have defined in space. So this one is what's called a helix. Sorry. You maybe heard double helix for DNA, so science connection there. But a helix is just a spiral, like a spring defined function. And so we can see that develop here. And then here, some different helices. So as we change it to the plural, and how those functions change. So they change by the coefficients. That's what's going to change the speed of that spiral. So as we think about calculus, different ideas that we've learned this year in calculus, our first big idea of calculus was limits. So we can take limits. When we take a limit on one of these vector valued functions, we take the limit of each part, the I part, the J part, and the K part. We would say that a vector valued function is continuous if all three of the parts are continuous. If there's a discontinuity in any part, then that makes the whole function discontinuous. For example, if it was in the J part, that's kind of defining our Y motion. If there's a discontinuity there, it took a jump at some point, and so that would cause a problem for the whole motion of the particle. So tangents, as we then thinking about our calculus ideas, we transitioned from limits into derivatives, and a derivative was the idea of taking the slope between 2 points as we limit those points to having a distance between them of 0 as we get those 2 points really, really close together, and then that creates a tangent. So we can find tangents by thinking about that idea of limiting or of derivatives. So when we take a derivative of a vector valued function, we're going to take the derivative of each defining part of the function, the f, the g, the h, as being the functions of the I, the j, and the k part. So we tend to think about motion as being a primary application of these vectored valued functions. So if we have a function r that is defining position, then when we take the derivative of that, the derivative of position is velocity. So we get a velocity function then. Speed is defined as the absolute value or the magnitude of velocity. And when we think about magnitude for vectors, we're not just thinking about absolute value in the sense of make everything positive. When we think about absolute value or magnitude of a vector, then we're thinking about length, finding the length of that vector. So the speed is the length of the vector, of the velocity vector, I should be specific there. Then acceleration is the derivative of velocity, or the second derivative of position. And we can find a unit vector by taking the velocity vector and dividing it by the speed. And we'll do an example of that. So we got a curve here where we could then, that red vector is defining r prime. So that's the derivative of position, that'd be the velocity. So it's the velocity vector at a particular time of 7 pi over 4. All right, so derivatives are going to follow the same rules as they have for our x and y defined functions here. It does start to get into some dot product and cross product rules there. We're not going to concern ourselves with those. We're just going to stick mainly with those sum and difference. All right. If r is differentiable and the length of r of t is constant, then r times the derivative of r is equal to 0 there. All right, so we're going to get into a few examples here. So let's start with limits. So if I have the limit as t goes to pi over 4 of the cosine of ti plus the sine of tj plus tk. To take our limit here, we're going to take our limit piece by piece of the vector. So our first strategy of limits was just try to plug in the number. And if you can plug it in and there's no problem, then that's your answer. If we run into a problem like 0 over 0, then we would need to maybe consider L'Hopital's rule or one of our other limit strategies. But as I just plug in pi fourths here to each part, so cosine of pi fourths I plus sine of pi fourths j plus pi fourths k. These are all things we can evaluate. So when we think about pi fourths is a 45-degree angle. So we end up with a 1 square root of 2 triangle. So 1 over square root of 2i plus 1 over square root of 2j plus pi fourths k. That would be our limit in this example. And you can leave them unrationalized like that with the squares in the bottom, or you could rationalize your denominators. Either way is fine. All right, let's look now at a position equation. So if we have a position defined by r is 2 cosine of ti plus I, looks a little bit like a j, it's an I, plus 2 sine of tj, there's the actual j, plus 5 cosine squared of tk. All right, so we're going to think about the motion of this particle. So it's an r function, it's defining position, so then we're going to do something that feels very natural and find the velocity, right? Position, velocity. So find velocity here. Velocity is equal to the derivative of position. So as we take a derivative here, we want to remember all of our derivative rules. So constant multiple 2 is just going to hang out. The derivative of cosine is negative sine, so I put that negative out front. Then the next piece, so when we take our derivatives, we just take them part by part, I part, j part, k part, using whatever rules we might need within those if we have products or chain rules or whatever. So then I've got 2 constant multiple, derivative of sine is cosine. And then 5 would be a constant multiple that's going to hang out, but we're actually going to need a chain rule on this guy because we have a cosine squared. So taking care of that squared, we're going to multiply that 2 down, leave the cosine alone, but lower the power, so it's a cosine to the first power now. But chain rule times the derivative of the inside times the derivative of the cosine derivative of cosine is negative sine. So I've got a negative then out in front of that. So I could just plus a negative 10 or replace the positive with a negative. Okay, so that would be our velocity vector function. If we wanted to find the speed, okay, so speed, so this was velocity. If we want to find speed, speed is defined as the magnitude of velocity, and magnitude is the length, not just make everything positive. So when we think about length, we're thinking about Pythagorean theorem, in this case a three-dimensional Pythagorean theorem, but that is then the square root of each component part squared. So when I square that first part, -2, that's going to become 4, and then sine squared of t, plus, and we don't do the i's, j's, and k's, those, because we're taking just the function part of it. Then squaring the middle part, 2 makes 4, and cosine squared t. And then squaring here, I'm going to have 100, positive 100, because squaring a negative becomes positive, and then cosine squared t and sine squared t. Okay, so a little bit of cleaning that could be done here. In this first part, we've got sine squared plus cosine squared, both multiplied by 4. Sine squared plus cosine squared is 1. 4 of them would make 4. So we could then simplify this down to 4 plus 100 cosine squared t sine squared t. Otherwise, there's not a ton we can do with it. There is actually a trig identity that we could have used back on that velocity function to replace the sine times cosine or cosine times sine. We could have replaced that in with a trig identity, but I don't expect you to really have those memorized, and it's not a necessary step. So we could just leave it right here. We cannot go back through and take the square root of everything. It's tempting, but because of that plus sign still, we cannot. If it was all a product, go ahead. But with that plus in there, we cannot. So one other thing we might want to do with this is maybe find acceleration. Acceleration is the derivative of velocity, or that would be the second derivative of position. So I'm going to look back to that purple velocity function, and I'm going to take a derivative there. So constant multiple -2, sine, the derivative of sine is cosine t, and that's the I part. Then plus 2, constant multiple. Derivative of cosine is negative sine, so now I need to throw a negative out in front of this. And now on this last part, we're going to need a product rule. So as I think about product rule on this, I'm going to think about the -10 cosine as being my first part of the product and the sine as being the second part. So when I do first, -10 cosine t, d second, now the derivative of sine is cosine, so I'm going to multiply by a cosine, so I'm just going to make that squared. Then plus second, that's sine, d first, the derivative of the first part, so it has that -10, and then the derivative of cosine is negative sine, so double negative, now that's a plus again, and a sine, so I'm just going to make that sine squared. Okay, so, and that all is our k part. So I need the parentheses there to show that that whole thing there, both of those parts of the sum are the k part of this function. All right, so position, velocity, acceleration are derivatives for vectors, just as they were for our x and y functions here. All right. Then if we wanted to find these at a particular point, say we wanted to find the velocity at time equals pi thirds, we could plug a pi thirds into that or something as well. All right. So let me know what questions you have about this as you get working, and I'll see you again soon.